Today I'm going to talk to you about addressable quantum gates, the model we made to talk about coherent control, basically indefinite causal orders in the quantum setting. First of all, we have to understand that the main idea behind quantum computing is to use physical possibilities to make programs more efficient from a time complexity point of view, to make faster programs. This formalism is mostly understood within the quantum circuit model, where you have wires corresponding to quantum data. Gates are applied to these wires in a specified order, and then the wires are measured. This control flow is purely determined classically. Classically determined. You first apply U, then V, or first V, then U, but you can't apply them in a superposition of orders. The gates are controlled by a classical processor. As a consequence, if you want to make, a data like alpha UV plus beta VU at the end of a circuit, you have to have several copies of those gates U and V. You can't express it in the circuit formalism, without having to make a copy. Whereas if we were to have a quantum control flow, we would be able to put somehow the initial quantum data in a superposition of applying first V then U, or first U then V. And this is what is done by the quantum switch. This is what we call indefinite causal order, because, the order of application of U and V is not definite. And the quantum switch is kind of a basic brick to have this possibilities offered to us, because the infinite causal orders have been proven to allow for faster programs than the usual normal definite classical orders of gates. So this quantum switch will be explained in the next part of the talk, how we represent it in our model. But with indefinite causal orders, we can also do more complicated stuff, for instance, superposing order of application of gates that are on different Hilbert spaces, like here, for instance. There are already other models representing infinite causal orders. Some of them are very mathematical, like supermaps, really close to functional models. Some of them simply add the quantum switch to normal circuits and make indefinite causal orders arise from this. Our idea was to stay really close to the circuit idea, but by adding one main thing, which are addresses. Addresses in a classical computer are basically places where you can store data, when you can store the result of a computation, and that can be addressed. Like you can send stuff here, and you can, it can refer to another address, and you can have pointers like this. Our addresses will be quantum, but we will be able to manipulate them like first-class citizens. It means, in the programming language community, that we can handle them like any other quantum data in a way. You can apply unitaries to them, you can superpose them, and we will see you can also send them from one place of the circuit to another. So now I'm going to present the model of addressable quantum circuits, which is basically our main contribution. Here is the very simple EPR pair creation circuit, maximally entangled pair. First you apply an Hadamard gate, then a CNOT. This little circuit may be divided into 4 parts that we will call sectors, which basically intuitively correspond to physical locations in space. In 2, Hadamard gate is applied on the first qubit. In 3, you have a CNOT gate applied, and in 1, 4, nothing happens. But with the textbook quantum circuit, the causality, the order in which those sectors are crossed by the qubits, is implicit. It's always from left to right. Whereas with our model, as this will be able to change, we have to add arrows. So with our model, for instance, the circuit before would be represented like this, with targets. Each sector targets one sector at most, or perhaps several in a superposition, and the data inside of it will flow to this sector during the transport step. So the AQC, it may be represented like this, but those gates in each sector, like this, don't change during the evolution. However, what will change is the data inside of each sector. As you can see here, there are several parts inside of each sector. One of them is the target. We already talked about it. For instance, it's the little number inside of the 2 here, inside of the triangle, that specifies to which sector the data will flow. Here, in the bottom left hand corner of the first sector is the quantum data initially. It's in the first sector. After the first step, it travels through the sector, then goes into the second sector, where Hadamard gate is applied, then into the third sector, where the C0 gate is applied, and then it goes to the last sector. And yeah, the AQC is finished. You see, sectors are divided into 5 parts. One of them is HT, is the target. One of them is, 2 of them are output spaces, where data will flow from to the targeted sector, if there is one. 2 of them are the input spaces that will receive data from a potential targeting sector. But there are also 2 other distinctions between normal quantum data, basically on what we are doing the computation, and the W here, the stored address space, where you can superpose addresses and send addresses to other sectors. It was not very clear in the first example what we were going to use stored address spaces for, but I'm going to explain it now. Initially, we may do the EPR pair creation circuit with such an initial state. You have 2, 3, 4 in the first sector, and 0 as a quantum data as usual, but no implicit orderings of the sectors. The direction in which the data will flow will be specified on the way, in a way, by the gate operators. After the first step, S as scattering, which basically is a synonym for gate operators in our model, the target of the first sector is fooled with a 2, and the addresses and data spaces travel to the output spaces of sector 1. Then during the next transport step, they are transported to the second sector, where here an Hadamard gate is applied and the address fills in the target sector, the target subspace of the sector 2. Then it goes into sector 3. We apply the same C0 gate as usual in sector 3, but we also move the address to the target, to target sector 4, where the data may flow during the next transport step. So the evolution consists in by alternating T and S, those operators. The evolution is purely synchronous. Basically, we apply a scattering, huge scattering unitary on all the sectors, and a transport on all the sectors during each step. The scatterings are basically gate operators, Hadamard or C0s, or anything that will superpose addresses depending on the data. The second step is a transport. This transport is explained here in a way. It swaps simply the input spaces of the targeted sector with the output spaces of the targeting sector. And with those 2 steps repeated indefinitely, our addressable quantum circuit evolves. Now I'm going to tell you how to implement the quantum switch, which is quite an usual thing to do when we're talking about indefinite causal orders. It simply consists in superposing the order of applications of 2 gates. If the switch qubit is at 0, first it's V. If it's at 1, first it's U, and then V. And if it's a superposition, then it will be a superposition of causal orders of those gates. So if we wanted to represent it like a textbook quantum circuit, in a way, it would be like this, with a gate U, a black box V, that will be superposed by a large gate QS, a quantum switch, that may encompass 2 sectors. And yeah, in our implementation, it does that. First of all, the quantum data is in this state at the beginning. You see, in sector 1, you have the quantum state, psi, and a control qubit, which is initially at 0 plus 1. Addresses are initially in sector 2. When the quantum data enters sector 2, here the superposition will happen. In fact, the superposition of causal orderings arises from superposition of addresses via superposition of paths, you will see. In fact, you superpose here depending on the state of the control qubit. If it's at 0, you do nothing on the addresses, and if it's at 1, you swap simply 3 and 4. I mean, the 2 first addresses. What happens is this. Then, during the remainder of the scattering step, it places the first address into the target space. Okay, so that it will have a place to flow during the next transport step. Then, at the end of the first scattering step, it looks like this. I did not represent the content of the target space because arrows already specify this. So then, after the transport step, each quantum data is in its corresponding sector. It will be applied U for sector 3, V for sector 4. And also, the target spaces are filled so that it may go into the next sector. Okay? It does that after the following transport step, and here it will be applied U in sector 3, V in sector 4 once again, and then it will flow into sector 5. Here it's not finished because those data in quantum data in sector 5 are still entangled with every targets in 3, 4, 2. It couldn't flow and be it couldn't interfere because it's still entangled with the quantum switch. So you have to send back those control qubits so that you can fold back this quantum switch into its initial state and then put back the control qubit in sector 5. During the next transport step, it simply flows to sector 6, and as it's not entangled with the quantum switch anymore, it may be applied any gate you wish without encountering any problem. Now I'm going to talk to you about how to manipulate addresses. In fact, I've been telling you that we were manipulating addresses like first-class citizens, but it doesn't mean that we are going to manipulate like exactly any quantum data. First of all, we ask for address spaces to be only finite sets. This is not a very big restriction. It's mainly because there is not a very huge need for infinitely large quantum computers at the moment, and it was making some proofs easier. Then on address spaces, we ask for two conditions. First of all, we want there to be no repetitions. Why so? Because else, the transport step would not be well defined. For instance, if a sector is targeted by two sectors, I remind you, the transport step simply swaps the input spaces of the targeted sector with output spaces of the targeting sector, synchronously over every sector. So this step would be ill-defined if there were somehow two sectors targeting one sector. So we forbid this. Then we ask there to be no address creation or destruction. Why so? First of all, this version of the addressable quantum circuits only features unitary evolution. And of course, creation or destruction of addresses is not reversible. I mean, yeah, without having garbage collection or stuff like this. And also, we have the problem of if we were allowing to create addresses in a local way, we could have somehow a creation of repetitions of addresses, and therefore the problem with definition of the transport step we already discussed. Now, for the last restriction on address spaces, the most interesting, is the potential restriction we have on gate operators. Okay, so as I told you in the beginning, addresses were initially understood to handle connectivity between sectors. Indeed, they specify to where the quantum data will flow. But it can be used, if we don't restrict, to do other things. For instance, if the sector targets 2, we could decide to apply, in a controlled way, the unitary U to the quantum data psi. Whereas if it targets 3, we could decide to apply V on the unitary psi. However, this is not exactly good from a conceptual point of view. Addresses should only handle connectivity. They are being designed for this. If you want to handle other things, do it with control qubits. And therefore, we can make external addresses indistinguishable. This is also physically justified because, with potential implementations of this, addresses would be done with kind of wires and distinguished to which faraway place this wire is going is a little bit difficult in a quantum fashion. And it's also a usual thing to ask in programming languages, for instance in Java or Camel. You are forbidding pointer arithmetics. You are not able to, the value of the pointer should not influence the output of your program. This is why we introduced the notion of renamings. Renamings are quite simply bijection over a set of addresses, transforming any address into the other in a bijective way and extended over a circuit space so that they can act also on qubits and superposition of addresses. For instance, if we swap 1 and 2, the following little part of a QC we represented here on the left becomes the one on the right. The sector 1 is now called 2 and has the address 1 in its target space. In the same way, sector 2 now is called 1 and has 2 in its output stored address space. Those renamings lead to the notion of nameblind scatterings or nameblind gate operators. A scattering is nameblind if it commutes with every renamings. Basically what it means is, for instance, if you apply the scattering S on addresses 1 and 2, and it swaps those addresses and applies the unitary U on psi, then if those addresses were totally different, for instance 2 and 3, it should do the same thing, swap the addresses and apply U and psi. Okay, so you can still do stuff on addresses, for instance swapping one with another, without even knowing what they are. Yeah, this is explained here with the example of having only 2 addresses. This is a general expression of a unitary gate on such spaces. You may, in a nameblind way, do exactly this. Either swap them with a kind of I sinus theta amplitude, or don't swap them with a cos theta amplitude. Those matrices, nameblind matrices, will be expressed in such basis states where we sorted those integers by ascending order. Those integers represent only words on addresses, okay? When you have all addresses present here. Those nameblind matrices, this is a general expression of such nameblind matrices on n addresses, where D is a nameblind matrix on n-1 addresses, and B a nameblind matrix on a semi-nameblind matrix on n-1 addresses. So it's a little bit more complicated, B, but we still characterize those matrices. And M1, M2, Mi are the same for every matrices. They are only renaming, swapping, for instance, Mi swaps I with I plus 1. So interestingly enough, the whole nameblind matrix may be deduced from only 2 blocks, diagonal blocks and a near diagonal block of size much smaller, because, for instance, if the nameblind matrix has size n factorial, D has size n-1 factorial. And you can do an induction on this to see what happens. But as the semi-nameblind matrices are a little bit more complicated, it's sometimes easier to work with pure nameblind matrices, where D and B are both pure nameblind matrices, meaning that they commute with every renamings. And their submatrices also commute with every renamings, and are exactly of the same form. So this type of matrix is easily defined inductively. You only have big O of 2 to the power of n real coefficients, whereas in a general case, you would have for such big matrices, a big O of n factorial squared coefficients. So now, if you have questions, you might decide to tell me them now. Or I could also talk about how this model fares in comparison to other models. Depends on, what time you want to give me. Perhaps I can first talk about this model. It depends on,
We did start a little bit late, so if you want to go quickly over this last part, I think that's okay.
Okay. So, yeah. The quantum causal graph dynamics is a model where, you have a quantum superposition of graphs, and it evolves according to local causal rules, in a way. So each vertex has both a local quantum state and a named port to communicate with other vertices. So our model also may be understood as a superposition of graphs that evolves causally, because the state of each sector only depends on the state of the sector at the previous step, and also potentially sectors of the same gate space if you have a gate space with several sectors inside. Or during the transport step, it only depends on the close sectors, the sector targeting it, or the sector that it's being targeted. And however, you have a little problem with connectivity. With our model, you may only target one sector and be targeted by one sector at the same time, whereas with this model, you may target more of those. So you have this little bit of a trade-off, because our model also has the possibility to store data a little bit more efficiently. But and also another link is that in both our models, vertices may be understood as physical locations. However, we shown that any AQC addressable quantum circuit could be modeled by such a QCGD, but the converse is not thought to be true in the general case, but we are trying to see what we could do to either prove or disprove this open question. And then we have supermaps, which is a really standard formalism to talk about indefinite causal order of gates. Here in this little drawing, you see you have several external operators whose order is going to be determined by a process matrix. This is a really functional point of view. In a way, it has been proven to encompass every possible physical evolutions, with CPTP maps and manipulating density matrices instead of purely unitary behavior. However, as it's very far from circuits, for instance, if you want to do something as easy as a loop, whereas in our model you can temporarily create simply a loop without having any causal problems, in this model you have to do copies and do it in a functional manner. So it's perhaps it's different in a way, a different approach to the same problem. And then there is also the PBS calculus, which is a graphical language modeling the control of purified channels, basically unitary matrices, and enhanced with ancillary from an environment, which basically means PPTP maps as well, maps and density matrices. It comes with a lot of completeness theorems, and the categorical approach, we are trying to do a little bit of the same thing by studying a paper by Kiribella, a diagrammatic approach to information transmission in generalized switches, so that we can relate our model from a categorical point of view to all the process theories and stuff like this. But back to PBS calculus. PBS means a polarized beam splitter. We can, of course, simulate the polarized beam splitter in our model. In fact, there is such a simulation in the full paper, if you wish to read it. And in the PBS calculus, obviously, you can do infinite causal orders, and the PBS, polarized beam splitters, come as a primitive. But a difference common with the supermaps is that PBS are only purely transient systems, where our system may also model memories and registers and things being stuck in a sector for long periods of time. So this is quite a big difference, because our system could model perhaps a full computer, running for a long period of times, and not simply a simple function or a quantum circuit, as usually. And also about outlooks, we are currently searching about how to implement CPTP maps, not only unitary operations within the AQC model. Basically, it's not going to be as hard as it could be, because we are already using vacuum states that are a quite efficient solution to answer to the usual problem of applying CPTP maps in indefinite causal orders. Because you see everywhere there are epsilons in our data, and this means nothing, but we are already representing them, so that shouldn't be too difficult. Also, the equivalence with vertex preserving QCGD might be possible. We are still studying this. And then categorical structure, I already explained it with the PBS. So thank you for listening, and I hope you have a lot of questions.